Okay, so now we're going to bring Klaus into the mix, who's going to be talking more about object storage. So, hey, Klaus.
Hi.
If you
Good day. Good evening.
good stuff. Let me share your screen. There's going to be a bit of inception there, but yeah, if you, I think you're.
Sure. I'll put up my.
Yeah, there we go.
There we
Okay,
go.
over to you, Klaus. I'll let you get started.
Yeah.
I'll come back in
Thank
at the
you.
end there, and if there's any questions, we'll be sure to ask then.
Yeah. Yeah.
Over
Yeah.
to
I
you.
have a section for it. So if my voice is a bit rusty and you can't quite understand what I'm trying to say, then just leave a question at the end, and we'll pick it up there. So yeah, I would like to talk about how to optimize small object storage. And how to deal with the problems that typically arise from that. I work at MinIO. Yeah, let's start by looking at what object stores are in general. So in large terms, it has mostly replaced file systems for cloud native, cloud wide, consistent concurrent storage. And yeah, it's really been a great innovation in terms of having storage available for stateless services that you're running either in the cloud or in the public cloud, in the private cloud, or in a hybrid cloud. So some of the most typical operations you see is getting data from it, putting data back into the to storage, listing, basically listing the various objects that exist, and then cleaning up, deleting objects. There's also some other features that aren't discussed as much. So one of the features that is very important is logging and immutability of objects. That could be from a legal perspective, that you need to preserve information for a certain period, but it could also be to protect against ransomware attacks, where you basically make it impossible to mutate data within a certain time frame. You have, as part of that, versioning, where you can roll back to previous versions of your objects that you want to read. You have life cycles that typically have things like cleanup of your data, in terms of if you have data that you don't need after a certain time period. It could also be deleting older versions after a certain time period. Things like that to manage your data. Don't have it ever growing, and basically having a bill that explodes for you. A lot of people that we are dealing with also find encryption to be really an important part for them, because they need to protect customer data, and they need to comply with various rules and regulations. Finally, replication is also a method used for either geo distribution or simply as a running backup of your data. If you're in the petabyte scale of data, then you don't really have instant backup of anything. So therefore, replication can serve that purpose for you. So yeah, let's talk about scalability and how to deal with scaling object storage. So I tried to lay out three of the the things that reduce scalability in a typical, or that can at least reduce it. So you have the scalability, the ability to scale to a huge cluster, and basically what you want is your performance to scale in a linear fashion with the hardware you add. That is an important part. That is well, it's basically the base requirement of scalability. For some people, it's good enough that you simply multiply or keep the performance that you have, but in some cases you also would prefer to get the extra performance that you get from adding more hardware and having more hardware available. Availability in itself is important, because the more hardware you add, the higher the chance are that some is going to fail, and you need to have consistent failover, and you need to be able to keep operating even if various parts of the setup is having issues. Finally, consistency is sometimes overlooked, but it's also at least when you're as application developer, you need to rely on a certain level of consistency. Basically, what are my guarantees for when an operation completes, that it is effectual and that it's stored on disk and isn't and you don't risk that it is actually not working. So typically, when you look at these, you take these factors and then look into the performance side, which is either throughput, basically how many gigabytes per second can I upload or download or from my cluster. How many objects per second can I retrieve? Basically, yeah, or upload, download. Also, you could run into synchronization bottlenecks, where you run into a limit to how much the cluster can synchronize, and in order to give a consistent view of your data. So just to give an overview of MinIO, just so you have an idea of what I'm talking about. So MinIO is a S3 compatible object store. It is available for private cloud, so you could run it on your own server. You can run it on public cloud instances. You could also do a hybrid cloud where you run parts on your own hardware and other parts in the cloud. It is erasure coded for high availability. So data is distributed across servers, and that ensures that you have availability. If some data, either a disk or an entire server, goes offline, you still have access to your data. There's no centralized database. Everything is persisted onto the file system, so you don't have to keep. You don't have inconsistency between different layers of a database. You don't have replication going on, so there's no lag or anything. You have the disks as your authority, and there's read after write consistency. which basically means that once you've got a reply, the object is written or deleted or anything like that, then any request following that will see that new state. So let's look at the small object case. So what are we talking about? Typically, when talking about small objects, we're talking about less than 10 megabytes, because the thing is that if you take big objects, gigabytes, then you're pretty much sure that you'll be maxing out your hardware, either your storage, your network, or something like that. With small objects, you stress all, excluding the network. So basically, you're stressing your storage, your CPU, and synchronization, all that part of it. In overall terms, we recommend hard spinning disks for large objects and SSDs for small. I think it's pretty obvious why, but on the other hand, it may not always be the hardware you are having to you have available. So yeah, looking at small objects, you have things like range requests, which can also give subsections of bigger files, which is sort of enables you to have smaller sections in a big file. So you upload a big file and you chug out parts of it, and the thing is, it's quite difficult to manage on the client side because you need to know where to look for each section inside the file, so you can build the correct request for that. So when dealing with small objects, we basically need to count IOPS, because the way you have to have high availability, you need to have several servers respond to the request, so you need to ask several servers, and that doesn't depend on the object size. So that's why the smaller they are, the bigger that part of the overhead then gets. So you for every small object you have, you will be hitting your physical storage on a number of servers. So there's various ways to cheat this. So you can have in memory parts of your storage. It's quite risky because you risk missing saves if a server crashes, or if the server simply fills up, then you can get into trouble that way. And the thing is, you're just creating a buffer that once that's filled up, then you're basically running into the same problem that you would have otherwise. So let's look at how we do this on MinIO. Then we place all objects on a file system. We don't have any special storage layer. We use standard Linux file systems, or even Windows or Mac if you do that. So data is placed into buckets, and you have a path where you place your object, and the storage on the file system simply reflects that. We have an Excel meta file that basically contains information about the object, the size and the checksums, headers, stuff like that. And then due to how S3 objects are split into parts, we store a file for each part. So what we did is that obviously the overhead of having the parts separately on disk for very small objects, it becomes quite big in terms of just inodes and extra blocks that you use. So we decided for small objects to simply inline the actual object data into the metadata file, so we're able to basically read metadata and return the data by simply opening one file on disk and reading that back. So some of these standard file system limitations also applies for us. So that also means you should create a reasonably separated path for your objects. Sorry. That way you don't have millions of objects in a single folder, because no file system can deal with infinite number of files in a folder in a reasonable way. You also have limitations like block sizes. Typical block sizes are 4K, so any file you store will take at least 4K, and so forth. So and of course, for every file you create, you are using inodes in or from your disk. So that's some of the things we've been dealing with in this. So one of the features we added is tiering, where we allow to offload the data part to secondary storage. We call that warm. So we have you can set up a hot tier where your data lands when it comes in, and then after a while the metadata is kept on the hot tier, but the actual file data is then tiered off to a secondary storage. So you're able to do all the operations on the metadata in a very fast fashion, but you don't have the huge penalty of having to keep all of your data on SSD, for instance, for forever. So other things we've looked into is API improvements that can help you. So there's a little advertised S3 API that is used for snowballs, which is the feature where you can order your data and have it delivered on hard drives. But it also has an API part where you can basically upload a tar file, and it gets extracted onto the destination as it's uploaded. So you're uploading a single file, but it ends up with potentially millions of objects on the remote. So it allows you to upload this many with just a single call. The strain for the server is approximately the same, because you have to store everything as individual objects. But it does allow the upload to take place with just a single call, which is usually preferred. We also added a zip extensions that allow you to list and read files inside zip files on a remote server. They are automatically indexed by the first operation that does it, and it's very performant. So you're basically able to extract a single file from inside a zip file with the same efficiency as opening a regular small object on the server. The files remain as a zip file on your storage. So everything inside it is controlled by this single file, which means you can replace everything atomically. So if you replace the zip file, then you're switching all of the files inside in a single operation. Similar to how the tar file upload requires a custom header, this also requires a custom header, just to be sure it isn't accidentally triggered by a client. So you add a header called xMinIO extract equals true. You upload your zip file. So we upload restaurants with the date. This is the prefix, and then we upload a zip file. We just call this ID 0 to 1000, and you can then use regular list object operation to list all the files inside this with a single operation, and you can request with get object any file inside the zip file. So yeah, it's quite space efficient, mainly because you don't have the overhead of all the individual objects. It allows ID to value lookup. So if you name your files with the ID of what you're interested in, then you can simply do an ID to value lookup and get the result. Obviously, you upload much faster than you otherwise would. You do it with a single call instead of thousands. It's easy to manage. All operations are done on the object. So sorry. And it's a well-established format. So there's no specialized code needed to create these. You can't do individual file updates inside the zip file. We keep a recommendation of around 10,000 files inside each zip. That's mainly to have the lookup be fast enough so you can still serve millions of files per second. It shares metadata. There's no unique metadata per file inside the zip, and it requires some minor client modifications. So yeah. So yeah, for servers, we recommend benchmarking for objects per second to see if you can hit the target that you're needing, and also consider the entire object life for this. We have seen people that have benchmarked and yet we can upload this many objects per second. Everything is fine. Go ahead. Then they figure out. But there's also we have to update or delete. Cleanup is pretty much as expensive as uploading. So unless you expect your data to live forever, then consider the entire life of the object. IOPS is king, so a write needs to hit disk and requires the physical head in terms of spinning disk to move or the electron rows to activate for SSDs. So there's no way to make physical disks move their heads any faster. So be sure to not have crazy, let's put it that way, expectations on what your storage can do. Provision ahead. You shouldn't provision, so you have to upgrade, keep adding new hardware all the time. It should be something like every second year. You should upgrade your storage in terms of capacity, and because otherwise you'll be having to do a lot of management for that. When writing clients, design for big objects. If it's at all possible, then avoid having too many small objects. You're making it much easier for whatever customers of your application there is to create a reasonable performing deployment. The bigger your objects are, maybe write a little extra if it can avoid you having to search for the information. Use the available tools. There's an S3 select API that allows you to retrieve data from CSV and JSON files based on queries can be helpful. The zip files I just showed you, range requests, or maybe the tar uploads, at least to make the upload big, well, more manageable. Let's put it that way. So yeah, that's what I have. Let's start if there's any questions.
So there's no questions, Klaus, but a great in-depth session around, like, I've learned quite a lot around some of the intricacies around object storage and some of the, more to the point, some of the considerations that you're going to need to really be thinking about when it comes to like designing and architecting that object storage, whether it be for like a stateless workload, but in general, I see a lot of object storage for backup targets as well. And I think some of the considerations are exactly the same, right? Whether they're whatever that workload, whatever that data type is, there's a lot more consideration in there that I gave it effort to. So
there's always when you get into the details, but yeah, it's there's a lot of important factors to consider when you're because if you aren't if you're doing it in a public cloud, you're paying for the same operations. So small objects will mean more requests back and forth, and will just make it more expensive. So it's the same issue, and yeah, the cost is just going somewhere else. so yeah, that's
exactly that. But amazing session. Thank you very much, Klaus. So
sure.
the session will be available on its own as well as part of the whole day or half day event as well. So we'll make sure that we're sharing that socially out there. But yeah, thank you very much, Klaus, and hope to see you again soon on another CNDM day. Thank you.
No problem. It was a pleasure.
Awesome. Okay, now just